Hello everyone, I'm Andrew. In this video, I'll introduce our tourist group practices for efficiently annotating large-scale image classification dataset. This is a joint work with Amlan Kar and Sanya Feather. Data has a tremendous impact on the success of learning-based applications. Much of the recent AI revolution comes with large-scale datasets. Many of them include classification tasks, which is what we focus on in this work. Simple as classification is, there are still a lot of challenges in annotating classification labels. First of all, we need to properly define label space. Data itself can be intrinsically difficult with high intra-class variation. Also, some images can be corrupted. For some classes, they require higher expertise to reach agreement. Lastly, no matter which platform you're using, having unreliable worker is inevitable. All of these challenges lies into different parts of the annotation process, and each part has different design factor. In this work, our goal is to provide insight on how different design choices affect efficiency without sacrificing accuracy. The design space is nearly infinite in the annotation process. In this work, we investigate 4 different directions, including ways to aggregate labels, how to use estimated worker skills, how to avoid over-annotating noisy data, what matters in modeling loop. Let's start from the background knowledge of label aggregation. Maybe the most straightforward way is to fix the number of annotations per image and take the majority vote as labels. There are a lot of datasets adopt this approach, probably due to its simplicity. A smarter way is to weight the annotation by their worker skill to reduce cost. For example, ActivityNet follow this to obtain robust annotation agreements. Note that for these two approaches, the total cost is usually linear to a number of images. We can further add a CV model inside the loop. Once the model learns some good features, we can achieve sublinear performance, saving even more cost. The sum lies into this category, but the annotations are only used to train the CV model. Automatic labeling such as open image is similar to this, but it does not annotate any data in the dataset, causing very noisy labels. Let's try to describe them more formally by using graphical model. Given a set of workers W and images with ground truth Y, a pair of them give us an annotation Z. We could only observe annotations and infer hidden worker skills and ground truths. This model is often called Darwin scheme model or DS model. We can move the DS model into its online variant by expanding the annotation set Z through time. When the CV model is added, we treat the model prediction as the prior over ground truth. In the following, we adopt this framework and explore different design factors of it. Under this framework, let's discuss the estimated worker skills. To estimate the worker skills, we follow Bayes' rule. We can estimate the prior of worker skills by querying gold standard questions. In the figure, the x-axis is the number of annotations per image, and the y-axis is the accuracy. We want to get high accuracy with low number of annotations. We explore using different types of prior, and find that the prior changes have evident improvement in fine-grained datasets, while it's marginal in coarse-grained datasets. Next, we move on to ways to avoid over-annotating noisy data. At every iteration, we separate the dataset into finished set and unfinished set by data confidence. We find that the accuracy saturates when the size of the finished set decreases for consecutive steps. Lastly, we move on to model in the loop. The learning problem in online labeling can be regarded as a semi-supervised learning problem. We can treat data in the unfinished set as unlabeled data, and propagate human efforts from finished set to unfinished set. We try 2 different semi-supervised learning approaches, pseudo-labels and mix-match. Pseudo-label reduce 70% number of annotation over prior work. At the beginning, when there is no annotation available, we can perform self-supervised learning to discover structures in raw images. This gives us drastic improvement compared to training from scratch, and we find that the advance in self-supervised learning can be gracefully transferred to online labeling. Since we use a model prediction as prior, the model output probability matters. We find that using clean calibration set to calibrate is very important. It reduces 42% number of annotation compared to using random sample calibration set. All the above experiments are done in simulation. We also provide experiments with human workers. By combining all the mentioned practices, we improve the efficiency by 50% over prior work. To summarize, we find that gold standard question helps in fine-grained datasets. We can perform early stopping by the number of competent images. Unlabeled images and self-supervised learning helps a lot. Clean calibration set matters. There are even more in our paper. Thanks for your watching.